Hello and welcome to this fun application of Hess's law. It's looking at choosing the best oxidizer for rocket fuels. So I'll start by giving you a little bit of basic background on what an oxidizer is in this context. I'm assuming that you have a working knowledge of Hess's law from your first year available chemistry. So this is really a sort of second year review of Hess's law rather than teaching about Hess's law from scratch. So looking at the basic physics behind a rocket launch, obviously you want it to travel upwards, away from the ground. But at the same time, gravity acts in a downwards direction, which tends to keep the rocket where it is. So you have to come up with something to overcome that gravity. So the rocket's engine provides something called thrust, and that acts downwards, and it causes propulsion as an equal and opposite reaction, when the propulsion acts upwards. So this is based on Newton's third law of motion, which states every action must have an equal and opposite reaction. So if your thrust is your action, your propulsion is the reaction. And you can see the arrows are the same size because the force is the same in each case. Now the idea is that in a successful rocket launch, the propulsion will be sufficient to overcome the gravity. So you can see the gravity arrow is smaller and the propulsion arrow is bigger. So a chemical oxidizer, in this case we're going to look at a liquid fuel. A chemical oxidizer is a compound which encourages fuel combustion. So it can either be liquid oxygen, obviously liquid oxygen is an element, or it can be another compound which has happened to be rich in oxygen. And one example that's been explored and used is dinitrogen tetroxide, N2O4. So obviously the N2O4 molecule has quite a lot of oxygen atoms locked up in it, so that's a good source of oxygen. So liquid fuels, hydrazines are commonly used. One example that's been investigated in the past is N,N-dimethylhydrazine. So the hydrazine part is the two nitrogens joined together, and the CH3 is the dimethyl part. And because both methyl groups are substituted onto the same nitrogen, we call this N, N in nomenclature terms. So here's our problem. We've got two possible oxidizers. We've got our N2O4, which we just talked about, and we've got straight liquid oxygen. So we're going to use Hess's law to investigate which one gives off the most energy and therefore is the best oxidizer. So first of all, looking at the data, it's delta FH. So the Hess's law diagram I'm going to use is based on that idea. So formation enthalpy. In other words, on the left-hand side, you've got the total of all the formation enthalpies of the reactants. And on the right-hand side, you've got the total of all the formation enthalpies of the products. And that will enable us to work out delta RH as our unknown value. So that little red arrow there represents an indirect route. And if we follow the arrow from left to right, it essentially gives us this expression here, where delta RH equals the negative of delta FH. So it's negative because the arrow is traveling in this direction, but the enthalpy arrow is pointing up. So we're traveling the opposite direction. And as we go around here, we're traveling in the same direction as the products. So therefore, that's plus delta RH for products. So let's do the first one. So I've converted that diagram in the top right hand corner into a version that has the actual equations there. So I've got my constituent elements in the correct mole ratios and standard states at the bottom. And if I just take the numbers from the data table and add them all up, I get these two values, and I can plug them into my expression, and that gives me minus 1997.7 kilojoules per mole for my N2O4. Okay, so having a look at the second equation, putting that into the same Hess cycle. On the left-hand side, I'm only going to use the value for N,N-dimethylhydrazine because oxygen is an uncombined element, so that's not included. It doesn't have a delta FH value. On the right hand side, adding everything up gives me minus 1865 kilojoules per mole, and putting that through my expression in the top right hand corner, that gives me minus 1913.3 kilojoules per mole. So therefore, obviously, this one is more exothermic. So as a result, the better oxidizer is N2O4, because more energy is released when the N-dimethyl-hydrazine reacts with that compared with when it's reacted with oxygen. Okay, hopefully this has been a useful look at this application of Hess's law. Until next time, thanks for listening and see you soon.